The quantum information theory part, this is the first part of the course, will be transforming from the ideas of bits into quantum bits. The quantum bits will be traced out in a circuit, in a called quantum circuit. And also you will see some of the quantum gates and the operations that can make this coherent evolution of our wave function represented by phi as quantum bits. You'll also see some of the entanglement, the importance of entanglement in communication, this known quantum teleportation systems nowadays, and also the decoherence, which is an essential part of quantum physics. The quantum physics nature is actually decoherent by itself. And once the environment is inserted into the picture, you will see environment models that are important for this information part. Also, the protocols for quantum information correction. We'll have sets of videos on this. And coding, why classical coding is different than quantum coding, and the challenges that made quantum computation at some point are hard tasks or hard problems to do, but now we have quantum coding and you will see how it works. So the approach of 9-qubit for sure is also involved in this picture. And let me tell you that eventually we have evolution of the wave function that we will trace, but this wave function can be represented in different, just expanding the Hilbert space, not only one phi. You'll see maybe parpartite state, you'll see kinds of these Hilbert space expansion. So the other part, which is also an interesting part, the quantum simulation part, is the involvement of many low energy physics backgrounds. You will see atomic physics, you will see condensed matter by engineering some Hamiltonians that condensed matter is interested in, and also some quantum gases. You will see cooling atoms, cold atoms, to form gases at the low energy mode and the ground state of a harmonic oscillation or harmonic oscillator. You'll see optical lattices, how can engineer optical lattices to build and to isolate atoms, and you will see quantum phases transitions at these optical lattices, and you will also see many-body perspective from these optical lattices, how you can evolve and get some new phases that you can tune during the interactions of these atoms in optical lattices. You'll also see quantum thermodynamics. You will see why thermodynamics at the quantum limit is different than classical systems, classical thermodynamics, and the governing laws for these actions. Also, long-range correlation. Once you introduce Rydberg atoms, you'll see long-range correlation, and the correlation is the essential part for building quantum simulation, because you work with couples of atoms maybe, or hundreds of atoms, at some point thousands of atoms, but the simulation will be built upon the isolation of those single long-range correlation approaches, and you will see maybe some perspectives of quantum field theory, the quantum field theory of Higgs. You will see the Higgs, the Anderson-Higgs mechanism, and how can we simulate the Higgs using quantum simulation. The last part, conclusion of this course, is about topological phases of matter. You will see topological quantum matter that is motivated for this year's Nobel Prize, for the last year, this year's 2017, the last year 2016 Nobel Prize in Physics with Dave Thouless. So we will be covering the part of the integer quantum Hall effect, and you will see why it's connected to quantum simulation. So the general scheme is the correlation function. You have correlation function between different sides, and this is the whole heart of building quantum systems into simulation. Thanks a lot, and let's start out our course by the second video.